It's your time.
Yes. Now, can I share now, or
Yes.
what do I need to do anything before?
Um, if you start your talk, please share your screen.
Oh, okay. Now, how do I share the screen?
So it's below, I think, in green, partager l'écran.
Oh, yes, indeed. So, share my screen here.
Et donc choisir le... Voilà.
Is it fine?
Fine, yes.
Okay. So, thank you very much, Anne and Pierre, for giving me the opportunity to honor Grégoire's memory. Thank also the Solvay Institutes for organizing this meeting. And in a sense, the work I'm going to present is also a consequence of the Brussels spirit, because it rests on a collaboration with Tarcísio da Rocha Filho from Brasilia, who got his PhD from Brussels years ago. And it is the Brussels connection which Leon activated to bring Tarcísio and me in contact. And then Moises was preparing his PhD at Brasilia, and our discussions evolved in the present result. So, okay, sorry, I'm sharing, but I have to switch my page. Yes. So, do you see the next page?
Yes, yes.
Okay, thank you. So first of all, I'll say a few words on a more personal theme, and then I'll switch to the technical work. Well, what made me start a PhD in Brussels and have such a good experience there was certainly the personality of Grégoire, who knew how to trust and encourage his PhD students and motivate their curiosity. Indeed, he started motivating my curiosity by handing me his lecture notes on the stochastic description of chemical reactions, which was not quite obvious to me from my training, but was a nice challenge. And the very next year, he brought me to another fascinating new area, which was the area of nonlinear phenomena in physics and biology, thanks to a summer school at Banff. And since then, well, I saw many more offsprings of his themes, which also irrigated our science. So he hit me at a soft point, the transition between deterministic dynamics and statistical physics, which is quite a challenge for all of us. And I appreciated his pragmatic approach to chemistry via stochastics and later on to complexity. In particular, being in Brussels was the opportunity to meet very impressive visitors and start happy collaborations, especially with Ray Capral and Harry Frisch. And what I must stress from this period is the importance of toy models, which is in fact a constant theme in physics. One very impressive and precursor aspect of his work in that period was the work on climate dynamics. But another aspect of Grégoire, which impressed me, was his very deep involvement in his family. And well, we all know how difficult it is to manage both the family aspects of life and the scientific ones. He gave a rather good example. So let me turn to my technical presentation. The aim of the work is to understand how a dynamical quantity, the largest Lyapunov exponent, behaves near a macroscopic thermodynamic phenomenon, which is a phase transition. So to keep matters simple, we start with a mean field system for which phase transitions are rather well understood. And this model will be in one space dimension, the unit circle. The particles have an angle and they rotate. They have a momentum p, and they undergo a mean field coupling with the interaction energy. Well, since it is mean field, you have the 1 over n in front of the double sum to keep it extensive. And the two-body interaction is the sum of two terms. One is a simple cosine, which makes the system ferromagnetic. Spins tend to have the same angle, but there is a second term which is also attractive with a Fourier coefficient equal to 2, a little à la Potts if you wish. But remember, we are on the unit circle, so the spin takes a continuum set of values. Now, the simplest case, delta equal 1, was introduced by Antoni and Ruffo, and it had a very beautiful career. It is the cosine Heisenberg-Millfield model. The version with delta between 0 and 1 was introduced by a Brazilian group, and they discovered a few more interesting behaviors. That is, first of all, let us recall the order parameters, which are the magnetizations. One is related to the simple cosine and sine of the angles, and the other one is the magnetization for the higher order term. And as a matter of fact, the dynamical equations of motion for a particle only depend on the total magnetizations. So each magnetization defines a kind of pendulum potential which tries to dictate its motion on each rotator. Now, the phase diagram is on the right-hand side, delta equal 1, rather simple. You have a ferromagnetic phase at low energy. You have a paramagnetic phase at higher energy. There is a second order phase transition at delta equal 1, energy equal 3/4. But if you reduce delta, you allow for the effect of the Q equal 2 term, and then things get more complicated. So you may have, for delta small enough, that is when the period 1/2 contribution, Q equal 2 contribution dominates, the lower energy phase is a nemagnetic phase. Now, between the three phases, nematic, paramagnetic, and ferromagnetic, you have second order transitions almost everywhere, except two critical points and a small range of deltas close to 1/2, where there is a first order transition. So that is all done in the microcanonical ensemble, not too hard. And here is a plot of the magnetizations for 4 typical values of delta. Delta equal 1, which is the simplest case. Delta equal 0, which is homologous to delta equal 1 by change variables. And for delta equal basically 0.35, you have a typical transition from first at low energy, the ferromagnetic, then you go to the nematic phase, and finally you end up in the paramagnetic phase when you increase your energy. For delta equal 0.5, you see the first order phase transition in the magnetizations. Now let me turn to the dynamics. Motion can be viewed for a mechanical system as a geodesic motion on configuration space. There are many ways to reformulate the action principle for classical mechanics, and Marco Pettini, Lapo Casetti, and co-workers used the Eisenhardt metric, which was rather suitable for the calculation. So a trajectory is a geodesic of that Eisenhardt metric 7, where U is the potential. You have to extend phase configuration space to make things a little simpler. And well, if you have geodesic motion, you expect curvature to play an important role. So you compute the Ricci curvature and its average. And when you consider the first variation equation for a trajectory, well, you expect to have the equation governing more or less the length of your perturbation vector. So the long-term behavior of that quantity will provide you with an estimate for the largest Lyapunov exponent. What comes out from the Jacobi evolution equation is that the coefficient in this second order equation, K of S, the curvature, can be or might be approximated with a stochastic process. So you assume a drift and a white noise contribution with quantities generated from the curvature. And after a few pages, you end up with your estimate where the two coefficients depend on microcanonical averages. Okay. For delta equal 1, all calculations are straightforward or almost so. You end up with quantities in terms of energy, temperature, heat capacity, and you find a critical scaling at the second order transition. Fine. If you try to perform the same calculation for smaller delta, then you need a Monte Carlo sampling because you can't work analytically, and you get such plots as these ones. Now for the Lyapunov exponent. Okay. Need transition, you get a simple scaling law. And what is interesting is that close to delta equal 1/2, for delta smaller than, say, 0.48, you have the second order transition, and then just above it, you have the first order scaling, but somehow the microcanonical Monte Carlo estimates do not stay at the expected value, close to 4%. They raise again before the tricritical point. Aha! So maybe the Monte Carlo estimates are not accurate enough. Wait a minute. Let us try trajectory-based estimates for the Lyapunov exponents. So now the simulations are in dots, and the agreement is not so good at all, in spite of rather heavy numerical calculations. So the conclusion is that, well, it may be that for mean-fit systems, the power law scaling can hold the largest Lyapunov exponent proportional to the distance to the transition to the power 1/6. However, we certainly need to improve on the analytical estimates to give a good account of the actual behavior of these systems. Well, I guess Grigor would have enjoyed such a topic. Thank you all.
Thank you. So are there questions? I have one question. So
Yes.
in the full phase diagram, so there are several lines of first order and
Yes.
one line of first order and several of second order.
Yes.
And the results about the critical behavior for the Lyapunov exponent is located around the central point, is it? Or
Yes, that is the most touchy domain. If you are far away from this first order line, in fact, scalings are fine. The difficult part is close to this first order line. There is work to be done.
so along the other lines, the result is known, the scaling is known.
The scaling fits better, but even for delta equal 1, the scaling is more or less okay, but there is room for much improvement.
Okay, I see.
In other sense, it is an open problem.
Okay. So are there other questions? So if not, let's thank Yves Elskens for
Well, thank you for the invitation.